Okay, welcome to Lecture 20. This is Chapter 5, Unit 2. We're going to be talking more about calorimetry. Okay, last time we spent a lot of time talking about math, the math of specific heat capacity, specifically. And now we're going to talk about why we care about it, and that is calorimetry. You see, measuring heat, the flow of thermal energy, heat, is a good way to measure changes in energy. So, for example, you have a container full of water, and you have a lot of stuff floating around in that water. And these things come together and they react. Okay, so you have reactants. Dissolved in water. Okay, when they react, they release heat. Okay? And that heat, causes a change in temperature in the water. So by measuring the change in temperature of the water, you're able to measure the amount of energy released by that reaction. And knowing about the amount of energy released by that reaction tells us a lot about the nature of the reaction. It takes us a couple steps further to get to how, particularly, that helps us understand reactions. But it's a really, really good, powerful first step. Calorimetry is one of those powerful tools that chemists have for studying materials and reactions. It's a really good deep dive sort of thing. And what precisely is calorimetry? Well, let's take a look at the word. Calorimetry. Okay. Break it down. What you have here is calorie and meter. Okay, so a calorimeter. We're talking about measuring heat. Okay. Calorie comes from calor. That's Latin. Just means heat. Okay, so we're just measuring heat with calorimetry. So calorimetry is about measuring heat, and we do that using a calorimeter. Okay, a calorimeter. Okay, that's the actual device. Calorimetry is the discipline. Okay. And so calorimeter measures heat flow into or out of a system. And system has a particular definition in science. So we have the system, which is just the subject of our study, okay? It could be as specific as, everything inside of a container. It could be a little bit more nebulous, as in, the reactants dissolved in the water, okay? In the previous slide, in previous example. Okay, the reactants would be the system, and then the water there would be the surroundings. Okay? So the system and the surroundings. And just so you know how much we care about what we're talking about, the system plus the surroundings equals the universe. So technically, for the math, it kind of matters. The system is the thing we're studying. The surroundings is literally everything else. Okay? So that together, they add up to the entire universe. So if you're talking about a chemical reaction, the surroundings are everything but the few grams of matter in that chemical reaction. Literally everything. But normally we can narrow our focus just a little bit and only consider the immediate surroundings. We don't need to worry so much about the influence of the chemical reaction on the sun or the next star over or the next galaxy over. We're not quite that big-headed. We just focus on the immediate effects. But it does matter for the math. So you'll remember conservation of energy, right? Energy is neither created nor destroyed. Okay, it can change forms, but it can't be created or destroyed. That means the energy of the universe is constant. So the total amount of energy contained in the universe is constant. It doesn't change. You can't get any more, can't get any less. Whatever there is out there is all we have. But if it's never changing, that means that delta E of the universe equals 0. If it were positive, we'd be gaining energy. If it were negative, we'd be losing energy. We're not doing either. So the change in energy of the universe is 0. That's what it means for it to be constant. But remember that the universe is equal to the system plus the surroundings. So delta E of the universe equals delta E of the system plus delta E of the surroundings is equal to, oops, stupid computer. Sorry about that. My computer wobbled on me. Is equal to 0. So we can now stop worrying quite so much about the universe as a whole and just focus on these two. And what this gives us is delta E of our system is equal to negative delta E of the surroundings. So equal in magnitude, opposite in sign. That's what you really need to focus on here. Never, ever forget about this negative sign. Always pay attention to where energy is coming from and where energy is going. Energy into the system is positive. Energy out of the system is negative. And it's going to be the exact opposite for the surroundings. Energy into the system is negative for the surroundings. Energy out of the system is positive for the surroundings. Okay? Because energy in means the system is gaining energy. So that means that the surroundings are losing energy. That's why it helps to have a simple and broad definition like this, because it means that if the surroundings are literally everything but what we're looking at, that means that you get this simple, stark definition. Equal in magnitude, opposite in sign. So pay close attention to where energy is coming from, where it's going to, okay? That will save you a lot of headaches. And never, ever, ever lose track of your negative signs. I once had a homework assignment in grad school. It was like 5 pages of solid math, just for the one problem. And it took me a couple of hours going over it and over and over it to find out where I was making a mistake. I knew I was making a mistake because I knew the answer was wrong. I knew what the answer should look like generally, and I knew the answer I was coming up with was complete garbage. And I couldn't find it until I realized that on like the second page, I had dropped a negative sign, and that's where I was screwing up. I was so annoyed, you have no idea. So pay careful attention to your negative signs. Save you so many headaches. So let's go ahead and, just really quick, go back to our previous example of the reaction. Okay. So we have our stuff dissolved in water. It's reacting, and it is causing the water to heat up. Okay, so change in temperature for the water is greater than 0. That means that heat is going from the reaction into the water. Okay, so delta E of the water is greater than 0. It's getting warmer. Heat is going into the water, which means that delta E of the reaction is less than 0. Okay, it's losing energy. The only way the water can gain energy is if the reaction is losing energy. Which means that we're talking about an exothermic reaction. Okay, that's why exothermic reactions cause things to heat up. It's because they're losing energy to their surroundings. Okay, so that's what I'm talking about with this equal in magnitude, opposite in sign sort of thing. And that's how you're able to get the energy of the reaction by measuring the change in temperature of the water. Okay, because we have the specific heat capacity of the water, we know how much energy it takes to raise the temperature of the water by that particular amount. So we know how much energy the reaction's releasing. All right, let's talk a little bit less about the background. Let's move on. What is a calorimeter? Calorimeters vary from very, very simple to somewhat more complex. But basically, a calorimeter is a chamber where you can control things, a thermometer for you to measure the change in heat, and that's all you really need. Now, they can get fancier than that. They can get a little bit more sophisticated than that. You know, a fancy $25,000 piece of equipment will also include an oven and, you know, a cooling device. So, cooling device and an oven. The cooling device usually just consists of something like liquid nitrogen in a tube running through the chamber. And the oven for putting heat in, the cooling device for taking heat away, and then a thermometer for measuring temperature so that you can do more stuff than that. But those aren't even really necessary if you're, careful. The simplest would be a coffee cup calorimeter. Calorimeter. Okay. Coffee cup calorimeter is literally just, pair of coffee cups stacked one on top of the other. Styrofoam is a pretty darn good insulator. So you can have stuff going on, inside your coffee cup. You stick a thermometer through the bottom of the coffee cup on top. And, it works pretty well. I mean, it's not a $25,000 piece of equipment, but it more than suffices for most of the stuff you'll be doing. Now let's do some scary calorimeter math. So let's say you have 50 mils of sodium hydroxide at 1 molar and 50 mils of hydrochloric acid, 1 molar. Each one weighs 50 grams, and they are at room temperature, 25 degrees Celsius. You mix these together, the final temperature is 31.68 degrees Celsius. How much energy in kilojoules per mole is released by this reaction? That looks pretty god-awful, but it's nowhere near as bad as you might think. First off, what happens when you mix 50 grams of water with 50 grams of water? You get a total of 100 grams of water. So we have a change in temperature, we have a mass. We can measure how much energy has been released into that water. Okay. Q of the water, the heat released into that water, is equal to mCp delta T. Okay. The mass of the water is 100 grams. The specific heat capacity of the water is 4.184 joules per gram degree Celsius. And the change in temperature is 31.68 minus 25.00 degrees Celsius. So what we have to do is we multiply all those together. So let me write it out a little bit more clearly. Put those in the back. 100 grams, 4.184 joules per gram degree Celsius, and 6.68 degrees Celsius. You multiply those out, and what do you get? That's 2.80 kilojoules. Quick stop. Is that number completely right? Okay. I did the conversion automatically from joules to kilojoules, just because I wanted to preserve significant figures. 3 sig figs. Okay. We have 5 here, we have 5 here at the mass, we have 4 here with the specific heat, we have 3 over here with the temperature. So the answer has to have 3 sig figs. That's why I converted it to kilojoules. That's all. But what about the sign? Should this number be positive? Should it be negative? Okay. The water is heating up, So heat is entering the water from the reaction. So yes, the sign of the water should be positive. Okay? So this is the answer that we should expect to see. 2.80 kilojoules. That is 2,800 joules. But we're not really interested in the water in and of itself. Okay, the water is a means to an end. Okay, what we really care about is the energy change of the reaction. But remember, delta E of the system is equal to negative delta E of the surroundings. And in this case, the reaction is the system, the water is the surroundings. That's why we care about those. So Q reaction equals negative Q of the water. So Q of the reaction is negative 2.80 kilojoules. But notice the discrepancy in the units. Okay, kilojoules versus kilojoules per mole. That is not a small distinction. Let's go ahead and clear this off real quick. So, Q of our reaction is equal to negative 2.80 kilojoules, but we need to find a way to get to kilojoules per mole. So we need to know per mole of what? Okay. We'll be getting into this in more detail, but for now, just accept that it's basically, this means per cycle of the reaction. So we normalize this, just like we did for limiting reagent problems. Okay. So what that means is that we had, you could focus on either reactant here, but we had 0.05000 liters of sodium hydroxide at 1 mole per liter of sodium hydroxide. It gives us 0.0500 moles of sodium hydroxide. So that's what we're really focusing on. If I were being mean, then I could turn this into a limiting reagent problem, and that would just make things a little bit more complicated. And I'm not doing that because the purpose of this is not to show you a difficult problem. The purpose is to show you how to solve the problem at all. But now what we do is we take our negative 2.80 kilojoules and we divide it by the 0.0500 moles, and that gets us negative 56.0 kilojoules per mole for this reaction. Because this is a simple reaction, just sodium hydroxide plus HCl goes to NaCl plus H2O, we can stop there because it's 1 to 1 to 1 to 1. We don't have to worry about any other stuff screwing up the calculation we just did. Okay. But for other things, yeah, we would have to take the coefficients into account. And don't worry, we'll be encountering that later. Isn't that nice? Okay, but for now, this right here, the 56.0 is our actual answer. And that is close to the real answer of negative 55.90 kilojoules per mole for this reaction, as has been measured by, the really expensive machines. That's not a coincidence. I set it up that way. But I think I will end the lecture here, leave you to ruminate on that. We'll come back and finish lecture 20 in the next one, when we'll be talking about bombs and losses. And no, it's not going to be nearly as exciting nor as poignant as you might hope. It's going to be quite dull, actually.